Basically, there are two types of transmission networks, point-to-point and broadcast or multiple access networks. There is not much problem in medium access for point-to-point because only two units share the link and are located at both ends. For broadcast or multiple access networks, the link or communication channel is shared by two or more stations or computers from workplaces, and two main concerns arise in this sharing. One is the efficient utilization of the channel with fair sharing, and two, a high degree of connectivity among stations. Stations access the medium through protocols, and these are what will be discussed here. There are four types of medium access protocols. The first is fixed assignment techniques, and there are three types. First is frequency distribution multiple access, or FDMA, wherein users are assigned and confined to a frequency band with a guard band in between to prevent overlapping. The second is time domain multiple access, or TDMA, which assigns a fixed time slot called epoch to each user with guard times in between slots to prevent overlapping. And the third is code division multiple access, wherein users have unlimited frequency spectrum and time slot access, sometimes referred to as spread spectrum multiple access. One such example is frequency hopping, wherein a station switches or hops from one frequency time slot to another, the pattern of which is determined by a binary code. There are advantages in using the fixed assignment techniques like collision-free transmission. However, there are also disadvantages like underutilization of channels since stations do not transmit messages at all times. The second type of medium access protocols addresses the disadvantages of the fixed assignment techniques. Random access techniques allow stations to transmit according to random requests for access to the medium based on the fact that packets coming from stations are coming out in bursts, bursty as it is called, and in irregular patterns. Although collision is eminent here, there are protocols to solve this problem. There are two types. Aloha with two types also, and carrier sense multiple access also with two types. Let's discuss Aloha. The first type of Aloha is pure Aloha, which was developed in 1970 by the University of Hawaii, and it means transmitting at will to a central station. If no acknowledgement is received, user station will transmit again. Channel utilization is only 18% due to collisions. The second type is slotted Aloha, developed by Roberts. Aloha time is divided into intervals called slots, and transmission of messages can only commence if it is at the start of a slot. Channel utilization increased to 36.8% due to lesser collisions. The second type is carrier sense multiple access, or CSMA. Allows stations to hear or sense each other. Each station knows when the channel is busy or not. Once idle, then the medium is accessed and message is transmitted. The two types of CMSA are the non-persistent CSMA with the following algorithm. You check the channel. If the channel is busy, do not transmit. You wait for a while according to a preset transmission delay, then check again. If the channel is idle, you transmit. If the channel is busy, you wait again, then check again, and then the cycle continues. Then the second type of CSMA is the P-persistent CSMA with the following algorithm. Check the channel. If channel is busy, do not transmit. You wait for the channel to be idle, then transmit immediately with probability P, meaning that there is probability that transmission is postponed. Then the third type of medium access protocols is the demand assignment techniques. There is central control techniques that require a central controller for allocating channels to requesting stations. And there are two types. One is polling systems, wherein the central controller goes from one station to another asking if there is something to transmit. The other is circuit-oriented system, wherein a station will request for a channel, and if there is availability, the central controller will assign that channel to that station, and all the other stations will be informed that that particular channel is busy. After using the channel, the station should send a deallocating message, and the channel is idle again. Another type of demand assignment is distributed control. Of several methods, we'll discuss only three. One is reservation Aloha, developed by Crowder and good for an unknown number of stations. Channel usage is divided into time slots and organized into groups. A station using a slot in this time group is guaranteed the same slot in the next time group until it stops transmitting. In round-robin reservation scheme, a station is assigned its home slot. After transmitting and the slot becomes idle, another station can use it. If the original station wants to transmit again, it has to cause a collision, so it will regain its original home slot. Then there's first in, first out reservation scheme. Channel time is divided into two types of slots. There are V smaller slots for reservation packets or small data packets. Then there are larger slots for data packets, which are assigned via reservations from the reservation slots on a first in, first out scheme. This was again developed by Roberts. Lastly, the fourth type of medium access protocol is the mixed modes and adaptive strategies. There are communication systems using slotted aloha for uplink channels and TDMA for downlink channels. There is also the reservation upon collision or RUC that makes use of slotted aloha and CDMA or TDMA to avoid collisions. In this module, we will be discussing the two most commonly used IEEE 802 local area network standards. First is the IEEE 802.3, which is the most popular local area network standard. It uses the carrier sense multiple access with collision detection medium access control method, and it allows a number of independent computers to communicate with each other. It has moderate to high data rate and consistently low error rate. It is usually owned by a single organization. Its medium access control sub-layer protocol is based on a one persistent CSMA CD LAN with the following algorithm. The physical layer specifications of the 802.3 is various cables are used depending on the standards such as data rate in Mbps and maximum segment length per 100 meters. The following table shows the most commonly used cables. For the parts of the frame, it should have a minimum frame size of 64 bytes, and it has 9 parts. It has the preamble, the start and frame delimiter, the destination address, the source address, the length field, and the logical link control fields, then the data, the pad, and the frame check sequence, which is a 32-bit CRC. For the IEEE 802.5, it is a token ring topology, and its medium access control sublayer protocol is based on a ring topology wherein stations are connected to form a loop and uses a ring interface to connect stations at various points on the ring, and it has 3 modes. First is the listening mode, the transmit mode, and the bypass mode. It has different actions of the stations and the ring interface. Then its physical layer specifications use shielded twisted pairs. It has 2 important frames, which is the token frame, 3 bytes long, and it is the second important frame is the MAC or the LLC frame. It has 11 parts: the start of the frame delimiter, the access control, the frame control, the destination address, the source address, routing information, the logical link control fields, headers, and then the data, the frame check sequence, the ending delimiter, and the frame status. The network layer is mainly concerned about the routes that the packet should traverse from source to destination. In this module, we will be discussing 2 routing algorithms, the shortest path routing and the distance vector routing, as well as internetworking and the Internet Protocol. Let's go to the routing algorithms. The shortest path means looking for a route with the least metric between the source and the destination. A metric may be the distance between 2 nodes or the average measured delay or queue length. We will not give specific examples here, but the idea is to find the shortest path from a starting node to a destination node in the least number of metric, least distance, or least hops. There are several algorithms, and the one by Dijkstra is widely used. Another routing algorithm is the distance vector routing. This requires each router to have a routing table or vector containing the best computed distance in terms of a certain metric to each destination and the path to use in order to arrive at that node. Now let's go to Internet working. Networks can be connected to each other to form a network of networks or an internetwork, which is called Internet for short. Because of the many types of networks, black boxes are used for Internet, and there are 3 common devices depending on which layer it operates on. The repeater operates at the physical layer, layer 1, and is used to amplify or regenerate weak signals by copying bits from one segment to another. The standard is 4 repeaters in one network. The second device is the bridge, which operates at the data link layer, layer 2, and it accepts data link frames from one network, transfers these frames to the data link layer for checksum verification, and then forwards to the physical layer on the other network. The third device is the router, which operates at the network layer, or layer 3, and is an intelligent device because it can decide whether a packet will be forwarded to another network or not, and this property makes it more expensive than bridges. Now, let's go to the Internet Protocol, or IP. IP is a connectionless service, and there are downsides. It does not establish connection prior to sending data. It just encapsulates and delivers the packet and does not even give the status of the packet. There are no error mechanisms for retransmissions. It is for the upper layer protocols to do these tasks for data reliability. The IP datagram has these functions. 1. It provides the basic unit for data transfer. It provides addressing, it facilitates routing, and it performs fragmentation. We'll discuss the first function, which is to provide basic unit for data transfer. The datagram is a unit of information that IP transfers, and communicating with other IPs on other machines entails embedding information in the datagram. It is divided into several parts. Version, which is this IP version of the datagram. The 1HL, which is the IP header length in 32-bit words. The type of service, or the TOS, which is the type of service that the host needs. The bits are read by the router for the appropriate route depending on the TOS indicated by an application. Next is the total length. The total length of the datagram, including header and data bytes. The maximum length is 65,535 bytes. Sometimes, datagrams or packets have to be fragmented because some networks have only up to a certain transmission size. The next is identification. It helps the destination host identify which fragmented datagrams belong together. The DF bit, meaning don't fragment, a message for the router not to fragment the datagram because the destination cannot put it back together. The NF bit, meaning more fragments, set on all fragments except the last one to indicate arrival of all fragments. Then we have the fragment offset, location of the fragment in the current datagram. Then the time to live, or the TTL, packet lifetime in seconds or more, commonly used in hops and decremented in each hop to prevent endless looping. Then we have the protocol, which identifies the higher level protocol that sent the datagram and the receiving protocol that should get it. Then we have the checksum, used to detect errors in the header, with the source and destination addresses, which indicate the network and host numbers of the origin and final destination of the packet. And then lastly, we have the IP options, used to extend headers for experiments. Now, the second function of an IP datagram is that it provides addressing. Addresses are usually written in dotted decimal notation, wherein every byte of the 4-byte IP address is written in decimal and separated by dots or periods, and each host has its own unique IP address. There is already a convention developed for IP addresses wherein the lowest IP address is, and the highest is. An IP address has two parts: the network address, the first 3 sets, and the host address, the last set. For example, in this IP address, this one is the network address, and this one is the host address. In internetworking, there is what we call subnets, an effective way to connect many computers or workstations, especially if they are physically connected to more than one network without requesting for additional addresses. This is done by assigning them their unique IP addresses by using a subnet mask and performing an AND operation with it to get the address of the subnetwork. Subnetting is an efficient way so that IP addresses can be optimized.